So what we're going to look at inside of today's lecture is we're going to look at power series. And a power series is a special kind of series in which what we have is instead of just a sequence or a series inside of a sequence where we have set values or set numbers, instead we're going to have these be functions of x. And they look a lot like polynomials because that's really what they are. They're polynomials. So power series, if we look here, is a series of the form n equals infinity, 0 up to infinity of Cn x to the n. And so what that looks like in this case is C0 plus C1x plus C2x squared plus, and we just keep going ad infinitum, okay? Where x is the variable and Cn are the constant coefficients. And so we're going to ask ourselves, well, where is something like this convergent, okay? And let's say, for example, if we picked all of our Cn's to be 1s, we'd get something like 1 plus x squared plus so on and so on and so forth. And what we'd end up with is a convergent sequence, or excuse me, a convergent series if x equals 1 or x is less than 1, and a divergent series if x is greater than or equal to 1. All right, we'll see some of those in a little bit. Or we could have a series of the form, the sum n equals 0 up to infinity of c to the n x minus a to the n. All right, and this one of this form is actually what we call a power series centered at A. So in the case of our first series, our power series is centered at 0, or at x equals 0. In the second one, the power series is centered at x equals A. Okay? And that is basically that if we plug in A, obviously we're going to zero out everything other than a constant C0, and we'll end up with 0. Okay? Actually, we'll even end up with 0 for C0. All right? Well, I end up with something undefined for C0. Excuse me. All right, but that's a power series centered at A. We have a power series centered at 0. So let's take a look at what are the things that we're going to be doing with these kind of power series and why are they so important? Because it turns out they're really important. They're really important especially for the approximation of difficult functions. So let's look at an example. And let's say, for example, that I have this. I have the sum n equals 0 up to infinity of x to the n over n factorial. Okay, x to the n over n factorial. And I look at this, and one is I want to notice that it's centered at 0. Okay? All right? And what this is going to end up being is this will end up being x to the 0 over 0 factorial, which is just 1, plus x to the 1 over 1 factorial, which is x, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, plus, and so on and so on and so forth, ad infinitum, forever and ever and ever, okay? And so what we get here is this would end up equaling 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24, right? And we just keep going forever. Or what we might end up with, let's say, for example, we take another example. And this one has x minus 2 to the n. So this is the sum, n equals 0 up to infinity, divided by, so this is x minus 2 to the n, divided by n plus 1 times 3 to the n. Okay? And what we'll see here is you can actually see that this one is going to end up here. We've got our x variable, all right, along with our n's, okay? And so this series is centered at x equals 2, all right? And all we really want to look at is we want to look at where is this power series showing up. Okay, so like say for example, this ends up giving us our first term is going to be 1 over 2 times 3, so 1/6 plus, and then we'll have x minus 2 divided by, and this will be 3 times 3, so that'd be 9, plus x minus 2 squared over, and this will be 3 times 3 squared, plus, oh excuse me, this should be 1 times 3, 1 times 1. plus x minus 2 times 2 times 3 to the 1 plus 3 times 3 squared plus, and so on and so on and so forth. And what you should notice, what the real big thing that I'm looking to point out here is that those are the powers, and hence that's the reason for it to be called the power series. Now the big question that we have then is, at what point in time do we know when the power series is going to converge, right? Because that's kind of one of the big questions that we have about power series is just in general. And in particular, we want to look at, like, you know, for what values of x are we going to get a convergent power series? Okay, so let's talk about that. We're going to have three options. One, the first option, is the series converges, okay, at x equals a, and then diverges for everything else. So that is that it only converges when it's on wherever it's centered, when x equals whatever it's centered at, and otherwise it'll diverge everywhere else. Two, we've got the series converges for all real numbers. X. And then three, we're going to have, there exists a real number r, greater than 0, such that the series converges if absolute value of x minus a is less than r. All right, so the distance between x and a is r, okay, and diverges if the absolute value of x minus a is greater than r, okay? At the values where, and we get absolute value of x minus a is equal to r, the series may converge or diverge. So what we want to do here, we're going to have some really important, there's going to be some really important questions or conversations, right? On the one hand, we're going to have either the series converges only when x equals 0, like when we are, basically right on top of the value x equals a, or we'll have a convergent sequence for, or convergent series for all real numbers x, or we're going to have this thing that we call a radiance of convergence or an interval of convergence, right? That's going to actually dictate for us for what values of x are we going to get a convergent series, and for what interval values of x are we going to get a divergent series. And so the remainder of this lecture is really going to be about how do we determine what that interval is, right? How do we determine what those values of x are that are going to give us a convergent series for the power series. So one of the things that we want to define here is this thing called the radius of convergence. So the radius of convergence is the value of r such that the series converges for all absolute value of x minus a is less than r, and diverges for all absolute value of x minus a greater than r. So what it looks like is that looks like that third component of that definition that we had about when we know something converges or doesn't converge. Okay, so what I want to imagine is that I've got an interval. Okay, right, and here's a, right, and this thing here, that distance is r. That distance right there is r. Okay, anything that's inside of that set of values, okay, inside of the values of r on either side of a is convergent. Anything outside of it is divergent. It's actually called the radius because when we think about it theoretically or set theoretically, or if we think about it, from a perspective of what we call measures, it is in fact an entire radius, right? Okay, it is that we kind of imagine these things as circles, and anything that's within that circle, or the radius of that circle, will end up giving us a convergent sequence. It's like our series. It's like the values kind of like just start to move within that radius. So what we want to get is we've got this thing, the center, centered at A, and then on either side of the center is going to be what we call basically is going to be called the interval of convergence. Okay, but this is our radius, and that's that distance right there. Okay, so we're going to have three different occurrences here. One, if r equals 0, then we have that first occurrence. Then the series is convergent only at x equals a. On the other hand, too, if r equals infinity, then the series is convergent for all real numbers x. And then we have the third instance, and this is the instance where r is a real number, not 0 or infinity. Okay? So if r is greater than 0 and less than infinity, okay, then the series is convergent for x minus a less than r, and we will have to determine separately if the series is convergent for x minus a equal to r. So we're actually going to have to, we'll know that for less than r it's going to be convergent, but for x minus a equal to r, we're going to have to figure that out. Okay? The interval a minus r less than x, which is less than a plus r, is called the interval of convergence. And how we get that is we get that by setting it up this way. We've got x minus a, right, is less than r, all right? And so consequently what that'll give me then is that'll give me x minus a is less than r, and then it'll also be greater than negative r, all right? So if you think about it from an absolute value standpoint, we add a to both sides, and we get a minus r, right, less than x less than a plus r. And that is our interval of convergence. So once we find the radius of convergence, finding the interval of convergence is fairly simple, right? It's basically imagining that you have a number line, you have a at its center, and then you're going to have the radius on either side. All right, so now let's take a look at finding the radius and the interval of convergence. So one, we're going to want to recall the ratio test. And that is, if the limit as n goes to infinity of a to the n plus 1 over a to the n is equal to L, and that's less than 1, then the series is absolutely convergent. On the other hand, if we have that same limit, and that ratio a to the n plus 1 over a to the n equals L, and that's greater than 1, then the series is divergent. And then if the limit as n approaches infinity of a to the n plus 1 over a to the n is equal to 1, then the ratio test is going to end up being inconclusive. So these are the three instances or cases that are going to be informative for us to actually go out and find the radius of convergence or the interval of convergence. Okay? So let's take a look at an example and see how this actually works. So let's take this example. The sum n equals 0 up to infinity of x to the n divided by n factorial. So what I'm going to do is I'm going to first use the ratio test or find the ratio. A to the n plus 1 over a to the n in absolute value. And so that's going to end up equaling x to the n plus 1 over n plus 1 factorial divided by x to the n divided by n factorial. Now this is going to then end up equaling x to the n plus 1 over n plus 1 factorial times x to the n over n factorial in absolute value. And then this will end up equaling, this is the opposite way around. This will be n factorial over x to the n. Pardon me. So this is going to then end up equaling x, because x to the n plus 1 divided by x to the n is going to be x, divided by, and then that bottom one is just going to be n plus 1. Okay? In absolute value. So, when is this, in fact, going to give us a convergent sequence? So I'm going to take the limit. I want to see the limit as n approaches infinity of x over n plus 1. Okay? X over n plus 1. Now, if I think about this, this is going to end up equaling, okay, x. Times the absolute value of limit as n approaches infinity of 1 over n plus 1. And that's just going to end up equaling 0. Well, 0 is less than 1. And so, no matter what value I pick for x, I end up with a convergent sequence. Or, excuse me, end up with a convergent series. That's awesome. Okay? So, there is, in this case, the radius of convergence, so r equals infinity, okay, because we have that second option. What we have here is we have a convergent series no matter what value of x we choose. So r equals infinity, and the interval of convergence is all real numbers. Let's take a look at another example. So again, we've got the sum, n equals 0 up to infinity, of n factorial x to the n. Right? Big difference here because our n factorial is now being multiplied by each power of x. Right? And so we might be asking ourselves, well, when is this actually going to be convergent? Well, let's start out. Let's find that ratio. So we're going to have a to the n plus 1, so that's going to be n plus 1 factorial times x to the n divided by, and this will be n factorial x, or x to the n plus 1, excuse me, x to the n. And so that's going to end up equaling n plus 1 times x to the n. Let's take a look. If we take the limit as n goes to infinity, excuse me, not x to the n, but just x. The limit as n goes to infinity of n plus 1 times x. Okay? Well, that's going to be x times the limit as n goes to infinity, okay, of n plus 1. All right? Well, that's a problem because this is going to end up equaling x times infinity, right, which is infinity. And so the series diverges except at x equals 0, which is where the function is actually going to end up being centered, right? Or, excuse me, where our series is going to be centered. And so consequently, right, that tells us that this series is in fact going to be divergent for all real numbers except for x equals 0. And the radius of convergence is r equals 0. All right, so what we've seen here is that if we end up taking this limit and it gives us infinity no matter what value of x that we select, then what we have here is we in fact have a divergent series, right, for all real numbers x. Just like in the previous example, we ended up with the series was convergent for all values of x. That gives me a radius equal to 0. Right? Let's take a third look, and let's look at one in which we see one where the radius of convergence is not 0, and it's not actually infinity either. let's take a look at this particular series. Let's say the sum n equals 0 up to infinity of x minus 2 to the n over n plus 1 times 3 to the n. So what we'll do is let's take a look at the limit as n goes to infinity and we're going to do a to the n plus 1 over a to the n. So this is going to be x minus 2 to the n plus 1 over, and this will be n plus 1, right? Because we've got to evaluate for all n plus 1. And then 3 to the n plus 1 divided by, and this will now be x minus 2 to the n divided by n plus 1 times 3 to the n. So this is going to end up equaling then the limit as n goes to infinity, okay, of, and this will be now x minus 2 to the n plus 1 divided by n plus 2 times 3 to the n plus 1 times n plus 1 times 3 to the n divided by x minus 2 to the n. So this is now going to be the limit as n approaches infinity, and we're going to end up with x minus 2 on top, okay, times n plus 1 divided by n plus 2, or divided by 3, right, because we're going to have 3 to the n plus 1, right, and we got divided by 3 to the n, so we got 3 times n plus 2 times x minus 2. Excuse me, that's not divided by x minus 2, but the x minus 2 actually goes away because we end up canceling out all but one of those. So we end up with 3 times n plus 2. And so now what we want to do is we want to actually analyze this and ask ourselves, well, what happens, right? What happens when we take that limit as n approaches infinity? Well, the first thing that I can do is I can pull out, I'm going to get x minus 2 divided by 3, okay? Or the absolute value of x minus 2 divided by 3, and times the limit as n approaches infinity of n plus 1 over n plus 2. And we'll just take it as proven that that's going to be then the x minus 2 divided by 3 is going to equal 1. Or excuse me, x minus 2 divided by 3 times 1. Pardon me. Now what we want to do is we want to figure out when does absolute value of x minus 2 divided by 3 equal 1? Because that's the threshold for the ratio test. The threshold for the ratio test is that when it's less than 1 we have convergence, and when it's greater than 1 we have divergence. Okay? So all we're going to do is we're just going to solve. We're going to get that x minus 2 in absolute value is going to equal 3, okay? And so consequently, r is going to equal 3. So that's our radius of convergence. R is going to end up equaling 3, right? It's when x minus a is less than r we have convergence. Well, when x minus 2 equals 3, we have x minus 2 over 3 equal to 1, okay? And that's that threshold for convergence. So when x minus 2 is less than 3, okay, that's when we're going to have convergence. Okay, so our series, the sum, n equals 0 up to infinity of x minus 2, okay, to the n divided by n plus 1 times 3 to the n converges when x minus 2 is less than 3. Okay? Now, what we want to do then is we know that this is when, okay, we know that for when r equals 3, this gives me that my ratio, according to the ratio test, is less than 1. Right? That's the first part there. That's actually, we know convergence for that case. What we have to do now is we have to actually determine, we need to determine if the series is convergent when r equals 3. So we know that radius convergence, we're going to say, okay, it's convergent for inside of that radius. What about on its edges? What about at the values for when r equals 3? So, if r equals 3, then absolute value of x minus 2 is equal to 3. And that means then that x is going to equal either negative 5, or excuse me, x equals 5, or x equals negative 1. All right, so we've got these two separate values. So what we're going to do is we're actually going to plug those into our series. So we're going to take the sum n equals 0 up to infinity of, we'll start with negative 1. Negative 1 minus 2 to the n divided by n plus 1 times 3 to the n. Okay. This is going to then be the sum n equals 0 up to infinity of negative 3 to the n divided by n plus 1 times 3 to the n, which is going to equal 3 to the n times negative 1 to the n divided by, excuse me, and that's still our series, the sum n equals 0 up to infinity, 3 to the n times negative 1 to the n divided by n plus 1 times 3 to the n, which is just going to then equal the sum n equals 0 up to infinity of negative 1 to the n over n plus 1. Okay? This is an alternating series. In fact, it's an alternating harmonic series, and it converges. So when x equals 1, okay, it's basically 1 over n, except it's negative, positive, negative, positive. You can check it. It's an alternating series. So when x equals 1, or x equals, excuse me, negative 1, then this series converges. So we're going to add that to our radius. It's going to actually end up inside of our interval. Let's check it then for 5. Okay? So the sum, n equals 0 up to infinity, of, and now we'll take 5 minus 2 to the n, divided by n plus 1 times 3 to the n, is now going to equal 3 to the n over n plus 1 times 3 to the n. And we're going to have that series now. Well, this is a very different series, given the fact that this is now just the series n equals 0 up to infinity of 1 over n plus 1. Okay? This series, on the other hand, all right, this series diverges. Okay? Because what we're basically looking at is a harmonic series where we have the regular harmonic series. So this series diverges as it is a standard harmonic series. So what that means is that when we write our interval of convergence, so r, our radius of convergence, equals 3, and our interval is going to end up being negative 1 to 5, but we're not going to include 5. Okay, so let's take a look at what exactly we did, and then we'll do another example, just to kind of clarify things. So, we looked up here, we started out, and we used that ratio test. And we used the ratio test in order to find the limit, right? And that limit, as n approaches infinity, okay, was going to end up being, in this case, x minus 2 over 3. So we found that limit, okay? Then we wanted to ask ourselves, when does that limit equal 1? Because that's going to actually set up our radius convergence. Well, we're going to get the absolute value of x minus 2 equals 3. Okay, and inside of that, that's going to be our inside of that is going to be our interval of convergence. Okay, and so our R ends up equaling 3. And you can see that this is that form that we've got earlier when we talked about when the series was going to converge. Okay, so whenever x minus 2 is less than 3, okay, we get the ratio would be less than 1, and we get convergence. Now the next part that we have to do then is we have to determine what about on the edges, right? What about the values when x minus 2 is less than or equal to 3, right? So when we have the equality of 3. And so what we do is we check each one of those endpoints, all right? If r equals 3, right, we check that one. We get the two values that will give us it equal to 3, that is x equals 5 and x equals negative 1, and we'll check them each individually. And it's possible, as we work, that each one's going to be different, right, for depending upon different values of x, okay? Depending upon the different endpoints, we might end up getting convergence or divergence, all right? Let's take a look at another example. So let's take a look at this problem. Let's find the radius of convergence for the sum n equals 1 up to infinity, x to the n over the square root of n, and we'll also find and the interval. We'll find both. So we'll take the sum, n equals 1 up to infinity of x to the n over the square root of n, and we're going to find that limit as n approaches infinity of x to the n plus 1 over the square root of n plus 1 divided by x to the n over the square root of n. And this is then going to equal the limit as n approaches infinity, okay? And what we're going to see is that this is going to end up being x, it's going to be x to the n plus 1 over the square root of n plus 1 times the square root of n divided by x to the n. This will then equal the limit as n approaches infinity of x over, and I'm just going to rewrite this as n plus 1 over n plus 1 over n. Right? So we basically just move in the n, we're going to divide through by the n. Okay? Well, this is going to then just end up equaling, this is n over n plus 1 over n, is going to end up equaling then x times, and this will be just x times 1. Okay? X times 1, which equals x. You can figure that out. This goes to 1, this goes to 0, right? So you just get x times 1 equals x. So when x, right, so the radius of convergence, okay, when rho, my ratio, is less than 1, the series converges, okay? This is rho. That's rho, okay? So x equals rho. So when x equals 1, when x is less than 1, the ratio, the series converges. Now all I've got to do is figure out, right, when the absolute value of x, absolute value of x is less than 1, right, the series converges. So all I've got to do is what happens if x equals negative 1 or x equals 1. All right, so let's check that out. If x equals negative 1, that is the left-hand edge of the interval, then we get the sum n equals 1 up to infinity, and this will be negative 1 to the n over the square root of n, right? Now, using our alternating series test, we can see this converges, right? Using the alternating series test. On the other hand, if x equals 1, then I get the sum of 1 to the n over the square root of n, okay, n equals 1 up to infinity, which is just equal to the sum n equals 1 up to infinity of 1 over the square root of n, which is a p-series with p less than 1. So the series diverges. So our row, okay, is less than 1 when the absolute value of x is less than 1. So that's my radius of convergence. Is r equals 1, and, okay, the interval of convergence is, we'll have include -1, but not 1. Because for -1, we get an alternating series, okay, and which passes the alternating series test. But when x equals 1, what we end up with is a p-series that is divergent. All right? So let's kind of just review some of the things that we've got here. All right? So when we're talking about and we're working with power series, what we want to do is we want to utilize that ratio test in order to figure out an equation for rho. Okay? An equation for rho. And then once we figure out what that equation for rho is, we can then actually put it in the proper form in order to find our radius of convergence, right? Basically, that x minus a less than r form that will tell us the radius of convergence. Also, don't forget that you're going to have to test. If you actually find a radius of convergence that's not equal to infinity or 0, you're actually going to have to test the endpoints of the radius of convergence. And how we do that is we plug it into the series and we see if that series is actually convergent. All right, so this ends the lesson on power series. Very interesting stuff, okay? All right, see you soon.